Okay. All right. We don't have a whole lot left. Just 4 sections to go. So 2 more in chapter 5, 2 in chapter 6. The homeworks for all of these are for all remaining sections are out there. Now I gave some slack in the deadlines because of the Hurricane Zeta and how much it affected students, particularly in the coast. So the homework deadlines pretty much extend to near the pretty much the end of a semester. So, and that's to give some flexibility. But I would keep in mind that we're going to have a final exam too. That's during the very last week, so after Thanksgiving. So very end of November, first few days of December, that'll be going on. So want to make sure that you get to each assignment before you take a final, because every section that will have been covered since test 2 will be in the final. Final is not comprehensive, so it's just covering material from chapters 3, 5, and 6. So plan accordingly as far as it's done. And absolutely everything needs to be in by the Friday of finals week. So Friday, December 4th is the absolute cutoff for anything. And then that way I have time to determine the final grades that'll do the that must be input into SOAR by the following Monday morning. Okay. The final exam is not ready yet. I'm working on it, and I plan to have it have the practice final exam available by a week from today, which will still be 2 weeks before a final itself is posted. So by then we'll cover just about everything, and you can try out the practice test. Okay. All right. Well, at least we had one more student show. Okay, so the last lecture I gave was about eigenvalues and eigenvectors, and we're going to continue with that today. So to refresh your memory from last time, if we have a situation like this, where A is n by n matrix, V is a non-zero, emphasis non-zero vector, and lambda is as a scalar. If this relationship is satisfied, okay, then V is an eigenvector of A, and lambda is the corresponding eigenvalue. But last time I did not talk about how you would find the eigenvalues in general, just in certain cases. So today you'll have a method for getting eigenvalues for a general n by n matrix. So if V is an eigenvector and lambda is an eigenvalue, and this equation is satisfied, that's just the definition, then I can go ahead and rewrite it this way, moving everything to one side. And V can be factored out to the right. So we have a situation where we have a matrix A minus lambda times the identity times a non-zero vector V is equal to 0. So anytime you have matrix times non-zero vector equals 0, that means that the matrix in question is not invertible, which is equivalent to this condition, but its determinant is 0. So this gives a way to find the eigenvalues of A, because what we could do is we could just work out this determinant, which will be a function of lambda. So lambda is a variable here. So you can write out this determinant, and then we have an equation that we can try to solve for lambda, and the solutions to that equation will be the eigenvalues. So this equation is called a characteristic equation. Now, this expression, once you actually work out what this is, happens to be a polynomial in the variable lambda. And if A is an n by n matrix, then that polynomial will be of degree n. So now you're solving a polynomial equation, and you would find the roots, and those roots are the eigenvalues. So now at least we have some kind of algorithm for obtaining the eigenvalues. You work out the characteristic polynomial by computing this determinant, which we know how to do, and then solve that equation. Now, solving that equation can be extremely difficult. Well, the problems that we're seeing here, it's something that's at least doable. Okay, so that's what this section is about: is getting the characteristic polynomial, and then from there getting the eigenvalues. So for this example here, we have a 2 by 2. So the characteristic polynomial will be quadratic. So we can certainly solve an equation like that. So here I take the matrix, and we're subtracting lambda times the identity. Well, the identity matrix is the matrix that has 1 in the diagonal and 0s elsewhere. So A minus lambda I just means subtracting lambda only from the diagonal entries. So here and here, only on a diagonal. The rest of the entries, these 7s, are not touched. So now we take the determinant of this matrix. So we multiply the diagonal entries and 9 minus lambda, and then minus the product of the off-diagonal entries. That's the minus 49. So then you work out what the polynomial is, and write it in its standard form. So this is the characteristic polynomial after you work out that determinant. So now, to find the eigenvalues, we need to get the roots of this quadratic. And this is one that happens to factor out nicely. So it's lambda minus 2, lambda minus 16. So by setting these equal to 0, we get the two eigenvalues, 2 and 16. So a 2 by 2 matrix is going to have, at most, 2 distinct eigenvalues. Those eigenvalues might be the same. They might also be complex. It just depends on the entries of a matrix. Any questions about this one? Here it's the same process. Find a characteristic polynomial from verify the eigenvalues. So subtract lambda only from the diagonal entries, then work out the determinant. So this times this minus this times this. And so this polynomial you need to multiply this out and condense it as much as you can. And this is a quadratic that we get. Now, this is one that does not factor nicely. So if it doesn't occur to you right away how to factor it, you don't want to bother with that kind of trial and error that factoring entails, you can always fall back on using the quadratic formula in this when you have a 2 by 2 matrix. So the quadratic formula is applied here. And sure enough, the numbers do not work out so nicely that we still have this radical here. So we wind up with -2 plus or minus the square root of -6. So those are the eigenvalues in this case. So then you would use MyLab's tools for helping you enter answers to account for the radical. Okay, here's a number that begins the same way. So subtract lambda only from the diagonal entries, work out the 2 by 2 determinants again. And what we get is something that does factor nicely, but it's also a perfect square. So it condenses into lambda plus 4 quantity squared. So then we set this equal to 0, and we get only one eigenvalue. So this 2 by 2 matrix has an eigenvalue that's of multiplicity 2. So it has two eigenvalues, it's just that they happen to be the same. So that's something that certainly can happen. And here's something else that can happen. Even when the matrix is real, when we subtract lambda from the diagonal entries and take this 2 by 2 determinant and clean all this up, we get this quadratic. And it's not clear that it factors nicely. So again, we apply the quadratic formula down here. And what we get is a negative number under the radical sign. So b squared minus 4ac is negative. So what we end up with is a pair of complex conjugate roots. So -7 plus or minus square root of 3 times I is the imaginary unit, square root of -1. Now, in MyLab's, for these problems, you're only required to enter the eigenvalues if they are real, or you check the option multiple choice question that it does not have any real eigenvalues. So real matrix can have complex eigenvalues that must occur in complex conjugate pairs. So it's always some real part plus or minus the same imaginary part. This is how polynomial roots behave. So these problems cover the different possibilities of what kind of eigenvalues you might get. So 2 that are real and distinct, 2 that are real and the same, or 2 complex ones. Okay, here we have a nastier one. It's a 3 by 3. So it's asking for a characteristic polynomial. And we have different ways of computing determinants. There's cofactor expansions. For 3 by 3, there's a rule of Saros that could be used. We've seen the determinant can be computed using row operations. So you reduce the matrix to upper triangular form. And then you can take a product of diagonal entries. But that's a bit cumbersome when your matrix has a variable in it. So what we're doing here is we take this matrix and then we subtract lambda from the diagonal entries. And what I've done here is a cofactor expansion. And there's different choices here. I've chosen the first row because we have a 0 entry there that we could take advantage of. It simplifies the algebra a little bit. So what we get is expanding along the first row, we have 1 minus lambda times the determinant of this 2 by 2 matrix that we see here. and then nothing, and then plus -1 times the determinant of this 2 by 2 matrix. It comes from deleting the first row and third column. So now we can deal with those 2 by 2 determinants. So 4 minus lambda times minus lambda minus the product of these two diagonal entries, plus the plus 12, and then plus -1 times the determinant of this matrix. This matrix is upper triangular, so the determinant is just a product of the two diagonal entries. And after that, it's just the tedious algebra to multiply everything out and combine like terms. It's a 3 by 3 matrix, so your characteristic polynomial is going to be a cubic, and this is what you end up with. Fortunately, this problem does not require you to obtain the eigenvalues. That would require taking a root of this cubic, which may be possible in some cases. For example, it might be possible to do something like factor by grouping, or there are some cases that happen to work out nicely where you can easily factor something out. But generally, that's a tall order, and there may be complex roots. But this is your final answer in this case. Here's another that is a 3 by 3. So you subtract lambda from all 3 diagonal entries. And here again, there are no entries in the matrix that are 0. So I just go with a default choice of a cofactor expansion. Along the first row. So minus lambda times the determinant of this 2 by 2 matrix. So minus lambda 4 minus lambda. Minus 3, remember the alternating sign pattern, times the determinant of a matrix you get by removing the first row and second column. So 3, 4, 1, and minus lambda. It goes here. And then plus 1 times the determinant of this 2 by 2 matrix from removing the first row and third column. So then you work out these 3 2 by 2 determinants in the usual way. And after all the expanding and combining like terms, this is your final answer of your characteristic polynomial. Finally, you're given a matrix such as this one, and you have to list just the real eigenvalues, accounting for their multiplicities. Fortunately, this matrix is particularly easy to work with as far as finding eigenvalues is concerned, because it's upper triangular. So anytime you have a triangular matrix, lower or upper, the eigenvalues are just the diagonal entries. So these 4 entries, 8, 5, 2, 8. So when entering them into MyLabs, make sure that multiplicities are accounted for. So the 8 is an eigenvalue of multiplicity 2, so it needs to be listed twice. So however many real eigenvalues you have, duplicates or not, that's how many you list here. That's really all this lesson is about. It's determinant of A minus lambda identity. We're subtracting lambda from each diagonal entry, and then in cases where it's a quadratic, then finding any real roots of this characteristic equation and then getting the eigenvalues. And as what happened in the last section, knowing that if matrix is triangular, the eigenvalues are just the diagonal entries. So are there questions about any of these? Okay, well, that's the end of this section. And then Wednesday, we will conclude this chapter with a section on diagonalization and factoring matrices using their eigenvalues and eigenvectors. I'll stop recording at this point.